Hello friends, in this video we are going to see the nature of velocity as well as shear stresses when there exists a flow of a fluid between two stationary plates. So let's move on to video. To check the nature of velocity, we will start with Newton's law of viscosity. So we can write it as tau is equal to mu du upon dy as per Newton's law of viscosity. We already know equation delta p by delta x is equal to delta tau upon delta y. So this delta tau upon delta y can be written as, this term can be replaced as delta p upon delta x is equal to partial derivative of this tau is nothing but the mu du upon dy. So it becomes, we all know mu is a constant, so mu into this second order partial derivative of delta y square. So it is clear that this term delta square u upon delta y square is nothing but the 1 upon mu delta p upon delta x. So integrating with respect to y, we have delta u upon delta y is equal to 1 upon mu delta p upon delta x into y plus c1. c1 is nothing but the integration constant which can be calculated by considering the boundary conditions and the nature of respective terms. So we have to again integrate it with respect to y so that we will have the clear values of the terms that we are interested. So again integrating with respect to y, we have this u is equal to 1 upon mu delta p by delta x into this y square upon 2, y becomes y square upon 2, constant c1 becomes c1 into y plus another constant introduced as c2. So we will apply boundary conditions. Say for example, if these are the two plates, then when y equal to 0, u equal to 0, we all know this y value is measured from this surface, this is y value. So at the edges, due to no slip condition, there exists zero velocity of flow. So if y equal to 0, u equal to 0. Putting this value, we will have this, if y equal to 0, this will become 0, this will become 0, this will become 0. So obviously the constant c2 will be equal to 0. To find out the value of this constant c1, we have to put another boundary condition when y equal to t, u equal to 0. So when value of y reaches to t, where t is nothing but the thickness of gap or distance between two stationary plates, these are the stationary plates, then it is also clear that for another plate having no slip condition, u will be equal to 0. So this 0 equal to 1 upon mu delta p upon delta x into t square upon 2 plus c1 into t. We will have value of c1 as minus 1 upon 2 mu delta p by delta x into this t. For further calculations, we will put value of c1 in the equation. So equation for velocity u will become 1 upon mu delta p by delta x into y square upon 2 minus 1 upon 2 mu delta p by delta x into t into y. So taking common term 1 upon mu delta p by delta x into this y, 1 upon 2 mu delta p by delta x, this equation becomes y square minus ty. So here it is also clear that this y square minus ty is nothing but the thing on which this velocity u is dependent. If we consider variation of u, it is clear that this is nothing but the equation of parabola. Hence, we can comment that value of velocity changes parabolically from edges and becomes maximum at center. So for these two plates, the variation of u will be something like this. So these are the value. Here this value is called as u max value. Again, we can find the relation between this u max value and average u or u bar. So we will continue with relation between maximum velocity and average velocity. So it is clear that velocity is maximum at y equal to this t upon 2, because we have already commented that it becomes maximum at center, means here thickness is, this distance is t upon 2. So just putting value of y equal to t by 2 in the equation that we have formed over here in this figure, this is very important relation. So putting value of y equal to t by 2 in this equation, we can comment as u max equal to minus 1 upon 2 mu delta p upon delta x. This minus sign means we have to alter the terms. So t into t by 2 minus this t by 2 bracket square. So 1 upon 2 mu delta p by delta x, t square by 2 minus t square by 4. So minus 1 upon 8 mu delta p by delta x into t square. This is the value of u max. We have find the relation between maximum velocity. We can find average velocity. For that purpose, we will consider total discharge divided by the cross sectional area. So average velocity u bar can be written as this discharge divided by area. We know that the distribution of velocity is not constant at all the locations along the width or along the thickness of the gap, but for simplicity purpose, for average velocity definition purpose, we consider that the velocities are same at all the locations, and accordingly we have calculated average velocity as this u bar upon q upon a. So basic assumption behind this is that velocity at all the depths are same, but actually it is not. So for that purpose we are going to define what is the relation between our considered values, that is u bar, and actual values, that is u max. So we will calculate it by considering small discharge dq, that can be calculated as velocity at distance y. Say for example these are the plates, so at distance y whatever will be the velocity, that is we will call it as say uy. So that velocity multiply by area of strip. We have considered this element ABCD, so we can note it as this dq is equal to minus 1 upon 2 mu dabba p by dabba x into this dy minus y square into this dy into 1. This dy, this distance is nothing but the dy, and three dimensionally speaking this is unit width 1. So I am hatching the area that I am considering. So this dy into 1, so it becomes dy into 1. So integrating from here, variation is in y changes from 0 to value of t. From 0 to t we have capital Q value, that is total discharge value, as integration 0 to t dq 0 to t minus 1 upon 2 mu dabba p by dabba x ty minus y square into dy into 1. So here we can write it as minus 1 upon 2 mu term as a constant. This dabba p by dabba x is also constant. This ty is having integration as t into y square upon 2 minus this y square having integration as y cube upon 3, and this whole bracket is having their lower and upper limits from 0 to small t value. Just putting the values of small t into the y term, we will have equation as minus 1 upon 2 mu dabba p by dabba x in bracket. This firstly we will put value as 0 minus we will put value as t, then this negative sign will get absorbed. So for that purpose we will alter the terms, so it will become t cube upon 3 minus t cube upon 2. So q can be written as minus 1 upon 2 mu dabba p by dabba x in bracket t cube upon 6. That can be simplified as minus 1 upon 12 mu dabba p by dabba x into t cube. Now we can find out the average velocity, that is u bar is equal to q by a. Here minus 1 upon 12 mu dabba p by dabba x into t cube divided by, in this case the area, total area will be this 0 to 2 and this width, so that will be equal to t into 1. So this t will just reduce the power of t by 1, so equation will be u bar is equal to minus 1 upon 12 mu dabba p by dabba x into t square. Now we are interested what is the ratio between average to the maximum velocity. So ratio of u max to u bar is u max upon u bar is minus 1 upon 8 mu delta p by delta x into t square divided by minus 1 upon 12 mu delta p by delta x into t square. It becomes 3 upon 2. Now let us talk about the significance of this term, why we are doing all these things, because it is very easy for us to calculate this u bar. We can directly calculate the discharge, that is, we can use a container of known volume in which the discharge is considered and time required to fill up that container. So that discharge divided by actual area that have been calculated, that gives us the value of this u bar. And now we can find the value of u max. This is the theoretical value u max by just multiplying 3 by 2 to u bar. So for simplicity in the calculations, we have derived this equation. Now let us see the shear stress distribution. Now we are going to consider the drop in pressure with respect to the distance, that is horizontal distance x. So for that purpose, drop of pressure head, that can be calculated by considering two plates having two different cross sections, say cross section 1 and cross section 2. Reference axis is, this is x and this is y. This is pressure P1, this is pressure P2, and it is clear that there exists the drop of pressure. Let us consider the values in x direction from origin as this is x1, this is x2. So we will have x2 minus x1. This L is nothing but the x2 minus x1. So we will start with basic relation, that is u bar equal to minus 1 upon 12 mu delta p by delta x into t square. Here the term delta p by delta x is nothing but the drop of pressure with respect to the x distances. So we can have relation for delta p by delta x as minus 12 mu u bar upon t square. So integrating with respect to x, we can have a relation as integration from 2 to 1, from this point 2 to this point 1. The pressure drop is delta p. This delta x will go on another side, will become 2 to 1 minus 12 mu u bar upon t square into dx. So solving integration, we can have this delta p becomes p, having its unit from 2 to 1. So pressure becomes p1 minus p2, that is equal to minus 12 mu u bar upon t square. This term was constant and dx becomes x. So putting these relations 1 and 2, we have value as x1 minus x2. But we know that this is nothing but the x1 minus x2 is nothing but the L having minus sign. So we will absorb that minus sign in writing. So p1 minus p2, that is equal to 12 mu u bar into L upon this t square. So this is the very important relation. We are interested in pressure drop. Pressure drop is nothing but the, in terms of water column height. So we will divide this P1 minus P2. So head loss HF is equal to P1 minus P2 upon rho g. So that is equal to 12 mu u bar L upon T square into rho into g. So this relation can be used, this is u bar, can be used to calculate the various terms. Now let us see the shear stress distribution. We all know the formula tau is equal to mu into w by y, tau equal to mu du by dy. So mu daba of y of, now u value is minus 1 upon 2 mu daba p by daba x in bracket ty minus y square. So in these terms, again we are taking common terms outside the bracket. We will have relation as mu into minus 1 upon 2 mu daba p by daba x into this t minus this derivative of this y becomes constant into 1, so t, and y square becomes 2y, so 2 into y. So it becomes tau is equal to minus 1 upon 2 daba p by daba x t minus 2y. When we are considering these plates, this is the value of y, this total thickness is T, and shear stress is proportional with the term T minus 2y. So it is clear that when y equal to 0, tau will be maximum. So putting tau max can be calculated as minus 1 upon 2 into daba p by daba x into t. So overall, if we want to represent the distribution of velocity and shear stress between the plates, say for example, these are the two plates which are stationary. As we have seen in derivation, this u max is at center and this tau equal to 0 at center. This curve is parabolic in nature and these curves are slopy or linear in nature. We will have 0 value of velocity at edges, at boundaries, because no slip condition exists at there. And as velocity is 0, it means that it is 0 due to maximum resistance, that is maximum shear stresses. So these are the points of tau max or tau node. These are the points of tau max. So at edges the tau max value will be obtained, and at edges velocity will be 0 and it will be maximum at center. That's all. Thank you.